Michael Christ, who is delivering the plenary address for our session. And Michael Christ is a professor at Berkeley and also a two-time ICM speaker. He's played a central role in the development of modern harmonic analysis, both directly through his own work. And as an undergrad, I remember learning about the Christ-Kisselev inequality, so plays a fond role in my heart, and also through the School of Mathematics that he's developed, both with himself and his former students, several of whom are present at the conference here today. So Michael Christ's talk is titled Oscillation and Frustration in Multilinear Inequalities, and this talk will be moderated by Polona Durkic. So Michael, when you're ready.
Okay, Josh, thanks. So first of all, I want to thank Josh and Malabika for the invitation. I'm delighted to be here on the Pacific Rim, and also the local organizers, my own colleagues, Alan Hammond and Fredun Reza Khan. All right, so my talk is about multilinear functionals and associated inequalities. And multilinear functionals, which act on tuples of relatively arbitrary Lebesgue measurable functions, are encountered rather widely in analysis. They arise, for instance, in nonlinear PDE, where they model interactions. They arise in Fourier restriction theory. They arise in the modern approach to Semiretti's theorem and related topics in additive combinatorics and ergodic theory. In the Sobolev inequality and related Holder-Braskamp-Lieb functionals. There's a little connection with Hilbert's 10th problem over the rationals, and there are surely many other connections. This selection reflects just my own ignorance and could surely be expanded. All right, of course, the foundational result in Fourier analysis is Plancherel's theorem, and a large part of its content is an inequality, which can be formulated as a bilinear inequality. So we integrate f of x times g of xi times a character e to the 2 pi I x dot xi, and in absolute value, that's controlled by the product of the L2 norms of the two factors f and g. This was generalized by Hormander in 1973. So Hormander's version says if you have any balls B in Euclidean space Rd, you integrate over the product of two balls, f of x, g of y, e to the I lambda phi of xy. And so that's controlled by a constant times a certain explicit negative power of lambda times the product of the L2 norms. This is for now of interest for large parameters lambda. So there's a lambda in the exponent here. And this is true provided that phi is non-degenerate in an appropriate sense. If you take the special case where phi of xy is just x dot y, and you make simple changes of variables, then this is in fact equivalent to Plancherel's inequality as formulated at the top. So these local inequalities with large parameters can give you a lot of information more globally. Okay, so in this kind of inequality, we have oscillation meeting structure. We have the factor e to the I lambda phi, which for large lambda oscillates very rapidly. And this ensures that if you integrate it over any ball of radius just a bit larger than 1 over lambda, then that integral is nearly 0. So there's very strong local cancellation that's encoded, that's produced by this factor e to the I lambda phi. But the inequality says that this cancellation is somehow durable, that after you multiply by f of x times g of y, where f and g are completely arbitrary measurable functions, you cannot destroy the cancellation. That nearly complete cancellation persists in the integral. And this happens no matter how irregular f and g may be. The thing that you can't do is multiply by a function that depends on both variables x and y. So this is the structural part. F of x times g of y has a particular structure. And I want to emphasize that this nearly complete cancellation up to the factor lambda to the minus dimension over 2, this is a global effect, global of course being in a bounded region, the ball across the ball. And we'll see this global effect as the talk goes on. Okay. So in this talk, we're going to consider integrals of products in the following form. We're going to integrate over a ball. And this ball in the talk will almost always be in R2, but occasionally in R3. And then we have a finite product of measurable factors. The measurable factors, however, are functions of fewer variables. And they will, in this talk, almost always be functions of a single variable. So I'm going to have fj composed with phi j. And it says down here that phi j is a map from R2 to R1. These maps will always be very smooth, and there'll be submersions, the maps Vj, but the Fj's will be simply Lebesgue measurable. And again, there will always be a finite product of such factors. Okay, so again, in this integral, you see structure. Each factor, Fj composed with Vj, has a very particular kind of structure. We have, one way to think of this datum is we have three foliations of our ball in R2, namely foliations by the level curves of the functions Vj. And each factor is something which is constant along the leaves of the corresponding foliation, but has completely arbitrary variation as you vary from one leaf to another. Okay, so those are the kind of functionals that I'm going to be interested in. And notice that there, despite my title, there is no oscillatory factor whatsoever. These are about as simple as you can imagine as far as functionals go. Okay, so the essential datum here is not actually the mappings, phi1, phi2, and phi3. Rather, you can think of these in various other ways. For instance, you can think of them as specifying a hypersurface in the Cartesian product of the domains of the three factors Fj. Each Fj on the preceding slide is a function of a single real variable. So the Cartesian product of the domains is three-dimensional, but we're only integrating over a two-dimensional region. So that two-dimensional region is a hypersurface in this three-dimensional set. And we're going to form this product of functions, and we're going to integrate it over such a hypersurface. Okay. Now, what matters is not the hypersurface itself, but rather an equivalence class, because what you can do is you can make smooth diffeomorphisms in the domains of the three factors Fj. And what we should really think about is the equivalence class of this hypersurface modulo the action of these three diffeomorphism groups. Okay, so that's really the significant underlying datum. It's not the phis themselves, but rather the geometric structure that they describe.
There is a quick question if there is a geometric obstruction, say if B is star-shaped.
I'm always assuming that my domain B is very simple, and I'm not really concerned with whether it's star-shaped or not, but the changes of variables we make will always be very smooth, in fact, real analytic. And so B will have, even after these changes of variables, a rather simple structure. Okay, so that doesn't really enter in. Okay, so the question we're interested in has to do with weak convergence of these products. So this is a question that was studied in a paper of Joly, Métivier, and Rauch, 1995, and they asked the following question. Suppose that instead of a single three-tuple of functions Fj, suppose you have a sequence of functions Fj comma nu. These are all in L2. They're functions of one variable, and we assume that they have uniformly bounded norms. Okay, so such a situation is subsequentially compact, and let's suppose that these functions converge weakly to some limits as nu goes to infinity. So that means the limits also are going to be in L2. And we have the same situation as described before. We have the mappings Vj, and then we form our products. Now we have a sequence of products, and we want to know whether this sequence of products, this product converges weakly as nu goes to infinity to the appropriate limit. So that's equivalent just to asking what happens if we let the ball B be arbitrary, or arbitrary within a certain region in R2, and does the integral over B of this threefold product converge to the integral of the product, the threefold product of the weak limits. Okay, so it's a question about weak continuity of multiplication, if you like. Okay, now Joly, Métivier, and Rauch were motivated by considerations in nonlinear partial differential equations, namely conservation laws, where you have certain a priori upper bounds. You get existence of subsequential weak limits just by weak compactness. And what you want to do is solve the equation for irregular initial data by solving it for very regular initial data and then taking weak limits. So in order to, so you get the existence of the weak limits just from compactness, but you want to know that the weak limit of the solutions is actually, again, a solution of the equation. And for that, you need this kind of weak continuity of the product. Okay, so that was the motivation for asking this question. Okay, now, and this is an important point for this talk, rapid oscillation is implicit in this functional. Namely, it's enough to prove the weak convergence in the case where each of the fj's tends weakly to 0, just by subtracting off the weak limits. And since we're working in a bounded region, if you think about the Arzela-Ascoli theorem, then you know that to have a weak limit of 0, that means that the bulk of the energy in the Fourier space has got to move off to infinity. So for very large nu, we have to be looking at functions whose Fourier transforms have the property that the L2 mass lives mainly at very large frequency, getting larger and larger as nu tends to infinity. So implicitly, there's an assumption here that the fj comma nu are rapidly oscillating for large nu. Okay, but it's not in a manner that's captured by any explicit oscillatory factor, e to the I lambda psi. So in that respect, the functionals I'm discussing are rather different from the multilinear functionals we're more accustomed to seeing in Fourier analysis, where we have explicit oscillatory factors. Here, the oscillation is implicit, and it's more complicated. Okay, so Joly, Métivier, and Rauch proved a very nice theorem. They showed that weak convergence does hold for threefold products in the setting I described under certain extremely natural hypotheses. Their hypotheses were essentially optimal. The main tool in their proof is something called microlocal defect measures, which I'm not going to mention again and not going to define in the present talk. And their proof was a proof by contradiction. The machinery of microlocal defect measures allowed them to form certain kinds of limits. If the weak convergence failed, then they could construct limits which have certain anomalous properties, and that eventually led to a contradiction. So their proof gave no quantitative bound whatsoever. Now, it's clear, just basically by functional analysis, that there has to be some novel quantitative inequality that underlies their theorem, but their proof gives no indication of what form it might take. Roughly, you have to gain something as the Fourier variable xi tends to infinity, and the question would be, what kind of function of xi do you gain? Is it a negative power of xi? Is it a negative power of log of log of log of xi? They were not able to say anything at all about quantitatively what's gained. Okay, now they were unaware that a few years earlier, Bourgain had actually treated a special case of their setup. Bourgain studied an explicit three-tuple of mappings. So x1 comma x2 goes to x1 by one function phi, goes to x1 plus x2 by another function, and goes to x1 plus x2 squared by a third function. And in that case, Bourgain had actually proved a quantitative bound, which I'll formulate on a slide that's coming shortly. And here I'm indebted to Terry Tao, who pointed out to me Bourgain's work, which seems to be severely underappreciated. In 32 years, it's been cited, I think, less than half a dozen times. But it is certainly a deep work. Okay, so back to the work of Joly, Métivier, and Rauch. They observed that linearity is an obstruction. And by linearity, I mean that the mappings phi j could actually be linear mappings. I'm only assuming that there's some real analytic submersions, but they could actually be linear. And Joly, Métivier, and Rauch observed that the weak convergence must fail whenever all three mappings are linear, and therefore must fail whenever you can change variables to make all three mappings simultaneously linear. And the way that works is this: the phi j's are linear functionals now, so they're linearly dependent because there are three of them in a two-dimensional space, so some linear combination vanishes. Okay, so I choose coefficients aj, which make the sum vanish, and then I set fj with a large parameter lambda to just be e to the I lambda times the Fourier character e to the I lambda aj times x. Okay, now for large lambda, the fj's are certainly rapidly oscillatory, and so they certainly tend weakly to 0. On the other hand, if you pull them back and multiply all three, then the product is identically 1, and so this tends weakly to 1. So the weak continuity fails. The weak limit is not what it's supposed to be. Okay, so that's an obstruction whenever the phis define a linearizable structure. And Joly, Métivier, and Rauch simply prove that there are no other obstructions. In all other cases, the weak continuity holds. Okay, so I'm dealing here with my dog who's crawling around at my feet. Sorry about that. So one can think about this situation geometrically, although it doesn't seem to actually help us. The datum phi1, phi2, phi3 defines what's called a web. So that's a three-tuple of pairwise transverse foliations of a two-dimensional region by curves. So you have three different foliations and leaves are pairwise transverse. And Blaschke had introduced a notion of curvature of such a web. It turns out that if you have real analytic structures, which I'm always assuming in this talk for simplicity, then non-linearizability of the three-tuple, phi1, phi2, phi3, is simply equivalent to this curvature of Blaschke not vanishing identically. So the hypothesis of Joly, Métivier, and Rauch had already been encountered in the literature. It's just the condition that curvature does not vanish identically. Okay, as I said, that doesn't really help, but it's interesting. Okay, so now here is a quantitative formulation of the theorem of Joly, Métivier, and Rauch. And it's theorem A of this talk, and it simply says that there is a Sobolev exponent S. S is strictly negative, such that whenever the associated web is real analytic and has nowhere vanishing curvature, the functional I'm interested in, the integral of the threefold product, is majorized by the product of the negative order Sobolev norms of the FJs. So for instance, this means that really you don't need to take these functions to be in L2. You can take them to be just slightly singular distributions. And this says that in a meaningful way, you can multiply three distributions of this particular type. Okay, now, if the curvature vanishes at some points but does not vanish identically, then you get the same conclusion. But now the exponent S depends on the particular three-tuple of phis that's given. In some sense, the more degenerate it is, the closer S has to be to 0. Okay, and this, sorry, I went ahead too fast. And this kind of quantitative result is exactly what Bourgain had proved in one particular case. If we go back to the first talk today, Zane Lee's very nice talk, there one was dealing with very particular inequalities where one was aiming for essentially optimal exponents up to an epsilon. In this theorem, there's no optimal exponent. The proof gives some particular exponent, but it's presumably a very bad exponent, nowhere near the optimum. And there's no good, even probably conjecture in general about what the optimal exponent might be. So that's not the spirit of this talk at all. Okay. All right, so in today's talk, I'm going to present rather basic elements of the proof, and I hope that this is in the process of becoming a theory with wider scope than what I'll actually say today. The theory has already been developed farther than what I'll say today and applied to bilinear singular integral operators and existence of patterns in vague measurable sets. This is quite recent joint work with Polona Durczyk and Joris Roos. And I think this will be one of the topics of the talk that Polona will give at this meeting tomorrow, Tuesday. Okay, and on the next slide, I indicate a further extension of what I've already said. Namely, I talked about a theorem for threefold products, but there is an analog for fourfold products. The setup is the same. You integrate over a two-dimensional domain, but you have four foliations, and you have four measurable functions, each constant along the leaves of its own foliation. The main hypothesis in this theorem, which is a necessary condition, is that if you add up the sum over the four indices, capital Fj composed with phi j. So again, these are just general measurable functions that are constant along the appropriate leaves. If this vanishes identically in some connected open set for some analytic functions, capital Fj, then the only way to do that is for those functions to be constant, the obvious way. Okay. Unfortunately, at present, there are certain auxiliary hypotheses in this theorem. In fact, there are four of them, and they're quite complicated to write down. Each of these hypotheses is, in a strong sense, generic. it's still a theorem of some scope. And I hope eventually that all four of those auxiliary hypotheses will be eliminated, but that is a task for the upcoming months or maybe years, we'll see. Okay, so I'm gonna move on to a couple other but related theorems. Let me see how I'm doing on time. So I'm gonna tell you theorems B and C as well. So theorem B is concerned with multilinear functionals where there is overt or explicit oscillation. So here I'm integrating over a three-dimensional domain, a nice bounded domain in R3. I have the explicitly oscillating factor, e to the I lambda times psi of x1, x2, x3. And that's multiplied now by a product of functions of the individual coordinates, xj. So I no longer have the mappings vj at all, or rather I just have the simplest mappings which send x to each of its three coordinates. Okay, again, lambda will be a large real parameter. Psi, of course, will be real valued so that e to the I lambda psi is rapidly oscillating. Psi will always be real analytic. The functions fj are merely measurable, and we put them in some LP classes with perhaps a different exponent pj for each index j. And what we want is an upper bound for our functional of the same form, a negative power of lambda times now a product of LPJ norms. Okay, so again, I have three factors that I'm integrating over R3, or a bounded region in R3 with an explicit oscillatory factor. And we're interested in what happens as the rate of oscillation goes to infinity. All right, so this is a question which of course has been much studied with some rather successful and somewhat technical work. The bilinear case has been very extensively studied, and there's been an emphasis on obtaining optimal decay exponents, lambda to the minus gamma, in terms of the Lebesgue exponents pj. There's a vast and deep literature which I can't even begin to summarize. But of course, Eli Stein was one of the leaders in this theory. Okay, for trilinear and higher degrees of multilinearity, there's a smaller literature, but there's still literature. There's a key paper of Fong, Stein, and Sturm. There's work of Julula, Gressman, and Shao, of Lee, of Gressman and Shao, and others. And they have also obtained optimal exponents gamma for certain kinds of phase functions in a certain regime of Lebesgue exponents pj. Okay, so again, rather precise results. However, since we're working on a bounded region, the strongest hypothesis on my measurable functions is simply that they should be bounded. They should be in L infinity. And the existing theory, although it does give optimal exponents for many combinations of exponents, already in the trilinear case, it very rarely, almost never, seems to give optimal bounds for L infinity. Okay, so although it gives the best exponent gamma, it doesn't seem to give, the existing theory doesn't seem to give the best exponent, namely the one you realize under the strongest condition on the functions. And as a benchmark for what I'll say, I note that in all general trilinear results prior to this that I'm aware of, the exponent gamma had always been at most 1/2. All right, so 1/2 is a benchmark for the trilinear case. All right, so here are some examples which I hope will be amusing. So again, we're integrating over unit cube in R3. We have e to the I lambda psi of x, and we have this structural factor product of fj of xj. All right. In the first example, I take psi of x just to be x1 times x2, the product of the first two coordinates. And then it turns out that the inequality is true with a lambda to the minus 1/2. This 1/2 is the best possible exponent in this example. But of course, this example is rather degenerate because my phase function doesn't even involve the third coordinate x3. Okay. All right, in the second example, we add a term, x2 times x3. So now all three coordinates come into play. And the exponent, not surprisingly, because the phase certainly looks less degenerate, the exponent goes up from 1/2 to 1. Okay, so here's a case where you can certainly beat the exponent 1/2. But this is, I have to say, this is an isolated example. I don't know any general theory that includes this example. This is a very special situation. Okay, And now we're going to make it even better. We are going to add the missing quadratic term, x1 times x3. So now we have all three possible quadratic terms. We have a coefficient epsilon, which is non-zero. And as soon as you turn this third term on, no matter what the coefficient is, the optimal exponent gamma goes back down. Very disappointingly, it goes back down from 1 to 1/2. So the optimal exponent we see is unstable here under small perturbations. And if you're an expert on this, and you've seen other theorems about these oscillatory integrals, I hope this is a little bit startling, if not outright shocking. We have a very strong example of instability here. All right, so that shows that we need to be a bit careful. All right, before we go on, we should note that there's a very natural equivalence relation among phases in this problem. So I'm imagining here that psi is a given phase, and I'm going to form from it a new phase, psi tilde, by adding a sum. Remember, J ranges over 3 indices, 1, 2, and 3. I'm going to add 3 terms, and each one is a function of one of my 3 coordinates, xj. And I'm going to take the functions capital Hj, of course, to be real valued, so I still have a real valued phase. All right, and now I'm going to look at the functional with the new phase, psi tilde. Okay, well, I have arbitrary functions here, fj, and I'm going to define new functions, gj. Gj is just fj times the unimodular factor, e to the I lambda, capital Hj. And that allows me to move those factors from this oscillatory factor over to here. So I have a new functional here with the original phase and with these new functions, gj, whose absolute values are identical to the absolute values of the original functions, fj. Okay, so the lesson is that as far as the size of this functional goes, these phases all satisfy exactly the same inequalities, psi and psi tilde. So they should be considered to be equivalent for our purpose. Okay, now I'm sliding over a technical issue here. When I say functions capital Hj, there are 2 natural kinds of functions to consider. One is real analytic functions, because that's what my phases are assumed to be, but the other is Lebesgue measurable functions. Those are more natural from the point of view of the change of variables we make. It's enough just to have capital H be Lebesgue measurable in order to go from the F's to the G's and vice versa. And in fact, both kinds of H's are relevant in the talk. So usually when I say equivalent phases, I will mean that the H's are real analytic, but as you'll see, the measurable H's will creep in towards the end of the proof. Okay. All right. So in order to state a theorem about this class of oscillatory integrals, I need a hypothesis, and it's going to involve this definition. I say that my real analytic phase psi is rank 1 degenerate. So these are the bad ones. It's rank 1 degenerate if there is an equivalent real analytic phase and some germ of hypersurface in my 3-dimensional domain, such that the gradient of psi tilde vanishes identically on this germ of hypersurface. Okay, now the gradient does not mean the gradient just tangent to the hypersurface, but I'm also allowing the normal component. Okay, so that's degeneracy. And degeneracy of a phase is naturally defined in terms of the class of all equivalent phases. Okay, it's a very easy fact, it's just a method of stationary phase, that if you have a phase that is rank 1 degenerate, then the optimal exponent in the inequality, the optimal exponent gamma, cannot be greater than 1/2. Okay, so rank 1 degeneracy is an obstruction to the kind of inequality I'm doing where I want to beat the gamma equals 1/2 benchmark. And the following example is very illuminating if you want to see what this definition means. So in fact, this is just about the very first example that I tried to understand when I went to look at this, this kind of functional. I wanted to beat 1/2 for the function psi of x1, x2, x3 equals the product x1 times x2 times x3, which to me looks about as non-degenerate as you can get. Okay, so if you take this particular example and you choose any number t strictly between 0 and 1, then you get an equivalent phase, psi tilde. Psi tilde of x is x1, x2, x3 minus t times the log of the product x1, x2, x3. Now, since the log of a product is the sum of the logs, this term I'm subtracting is a sum of functions of the individual coordinates, x1, x2, and x3. So this psi tilde really is an equivalent phase. If you calculate the gradient of psi tilde, you discover, disappointingly, that it vanishes. All three components vanish on a certain hypersurface, h sub t, which is just defined by x1, x2, x3 equals t. Okay, so first of all, this phase x1, x2, x3 is rank 1 degenerate. It's a bad phase for my purpose. But second, t is completely arbitrary, and the hypersurface along which the degeneracy becomes visible depends on the parameter t. And so you see that this rank 1 degeneracy is not something where you can say where the phase is rank 1 degenerate. It's a more global property. And particular elements of the equivalence class, the associated equivalence class of the phase can reveal this degeneracy in different places in the X space. That's a little bit weird, but that shows you it's a little bit of a complicated notion to work with. Okay, so here's theorem B. We're integrating over our three-dimensional domain, and we have e to the I lambda psi of x. We have the product of functions of the individual coordinates. And now we have the main hypothesis, which I've essentially already advertised, which is that my phase is not rank 1 degenerate. Okay, so again, if it is rank 1 degenerate, then the conclusion I'm going to state is false. So this is a reasonable hypothesis. Then we have an auxiliary hypothesis, which is that we look at the mixed second order derivatives of psi, d squared psi, dxj, dxk, for j not equal to k. And I assume that each of these is nowhere vanishing on my domain. So this is an auxiliary hypothesis, which I hope one day to weaken. And my student, Zero Joe, is currently working on doing exactly that. I don't think that this in its full strength is necessary. But anyway, it makes the proof work. Okay, so the conclusion is exactly what you're guessing I'm going to say, that we have a majorization for our functional by lambda to the minus gamma times the product of the L infinity norms of the Fs. I told you that I'm ultimately interested in imposing the condition that the FJs are bounded, so that's what I'm doing here. And we beat the benchmark. We get a theorem with gamma strictly greater than 1/2. Okay? Again, it would be of interest to pin down the optimal gamma, but the analysis I'm going to show you just doesn't come close to doing that. Okay, so that remains open in essentially all interesting cases. Okay, so that's theorem B. Again, we gain a negative power of lambda, but now it's a somewhat specific power, strictly greater than 1/2. Okay, so I had a very interesting experience. I was working on this project. One day I was sitting in my office at my desk, and I was in the act of writing down the final details of the proof of this theorem B, which I just told you, and there was a knock on my door. So it was my colleague, Craig Evans, and he told me about the work of Joly, Métivier, and Rauch, which I was completely unaware of at that point in time. And he asked whether maybe there was an inequality and whether it could be understood through Fourier analysis. And at first we had a nice talk, but I didn't have anything really to say. And then I realized a few hours later that I did know what to say. And then in fact, the quantitative version of the Joly, Métivier, Rauch theorem is an immediate corollary of this theorem B, which I just told you. All right. So I was writing the proof and didn't know it when I was asked the question. All right, so here's how that works. Let lambda be a large parameter and consider the part of F3 whose Fourier transform is supported where Xi has order of magnitude lambda. By just a partition of unity in the Fourier side where you cut according to dyadic values of lambda, we can reduce to this case. We have a multilinear functional. We just have to sum over the various powers of lambda, various values of lambda. Okay, and then we write F3 in terms of its Fourier transform in the usual way, and we compose with phi3. So F3 composed with phi3 of x is the integral of Fourier coefficients F3 hat times e to the I xi times phi3 of x instead of x, xi. Okay, so we get a representation of F3, and we insert that into the trilinear form. Remember, in theorem A, we're talking about a trilinear form that's defined by integration over a two-dimensional region, but now I put in another integral, so now I'm integrating over a three-dimensional region. I want to make that three-dimensional region independent of lambda. So I substitute xc as lambda times a new variable, and I call that new variable x3. And now I'm integrating over 0, 1 squared across a subinterval of 0, 1, exactly as we're doing in the theorem B, where we integrate over 0, 1 cubed. Okay, now you have to do some bookkeeping. There's Plancherel's theorem, and there's also a Jacobian from the change of variables. And if you take those two things into account, then what you find is that you lose by this reduction, you lose the factor, and that factor is a positive power of lambda, and it's a specific positive power. It's lambda to the 1/2. Okay, so this reduction of theorem B to theorem A, theorem A to theorem B, leads us to the kind of thing we study in theorem B, but we are losing lambda to the 1/2, and so we have to gain it back. And fortunately, theorem B gains strictly more than lambda to the 1/2. You get lambda to the minus gamma. Gamma is strictly greater than 1/2. So the gain outweighs the loss. The net is a negative power of lambda, and now you can sum that over dyadic values of lambda to conclude the proof of theorem A. All right, so here we see that this benchmark gamma equals 1/2 is really an important benchmark with some intrinsic meaning. It's not an artificial thing at all. Okay, so again, theorem B implied theorem A. All right, so I'm going to move now to theorem C, in which the two structural elements we've discussed so far are combined. So in theorem C, we're going to have a trilinear functional. It depends on a large parameter lambda, and there's going to be a phase. We're integrating now over R2 again, not over R3, and we're just integrating over a ball. We have the explicit oscillatory factor, e to the I lambda psi, and we have a product now, again, of three factors, fj composed with vj. So we're back in the situation where we have the three pairwise transverse foliations with functions constant along the leaves, but now we combine that with the explicit oscillatory factor. Right, so this looks like it might be a little more complicated than theorems A or B individually. And the theorem says, again, we gain a negative power of lambda times the product of the L infinity norms under a very natural hypothesis. That very natural hypothesis is that the phase psi cannot be expressed as sums of three functions, each of which is constant along the leaves of the appropriate foliations with real analytic dependence on the leaves. Okay, if psi can be expressed in this way, then as in the linear Joly, Métivier, Rauch example that I showed you before, one sees immediately that there's no decay at all. You don't gain a negative power of lambda. You don't gain a negative power of log lambda. You just can't gain anything whatsoever. So this hypothesis is certainly necessary for the conclusion to hold. There are also implicit hypotheses, which I haven't stated here, that the phis are real analytic, psi is real analytic, the leaves of the foliations are pairwise transverse, etc. Okay, so that's theorem C. Okay, and so I have, I think, about 20 minutes to go. In the remainder of the talk, I'll try to tell you a little bit about the main elements in the method of proofs. The proofs of all three theorems, A, B, and C, do rely on common elements. Although the statement of theorem C is a little bit more complicated, its proof is actually a bit simpler. And so that's why I've chosen to discuss the proof of theorem C. So again, theorem C is about trilinear functionals. We're integrating over a ball in R2. We have the explicit rapidly oscillating factor with a large parameter lambda. And we have these three measurable factors, each of which is constant along the leaves of an appropriate foliation. Okay, I'll discuss the proof, but I'll only discuss the key case in which the tuple of mappings Vj is not simultaneously linearizable. The linearizable case with this oscillatory factor is included in the theorem, and it was already treated by Lee, Tao, Thiel, and myself 15 years ago. So that case is already known. Okay. I'm going to use microlocal analysis, which I like to fancifully think of as quantum splines. So we start here with just a single function defined on the interval 0, 1. It's measurable and complex valued. And we're going to partition its domain into small subintervals of some equal lengths. I called them 1 over L rather than L. Sorry about that. On each small subinterval, we expand into a local Fourier series. So we expand F as a sum. There's a sum over Fourier frequencies K. K runs over the integers. There are Fourier coefficients little a, and there are the Fourier characters e to the 2 pi I k times y. And there should be a factor L here in the exponent that compensates for the fact that the length is not, depends on L. Okay, and I want to think that little f is really e to the I times capital F, and I want to think of capital F as being a spline. So capital F would be linear along each subinterval, but here little f is a general function, and so what I want to do is I want to think of each k as being a kind of local slope for 1 over I times log of little f, that is for capital F. It's a kind of local slope. But what I want to think is that all the slopes actually occur, and each comes with a certain complex amplitude, which is the Fourier coefficient A and K. Okay, so this is basically the picture of quantum mechanics where you have a superposition of eigenstates, each coming with its own complex amplitude. And of course, what we know from Bessel's inequality is that the sum of the squares of the coefficients is controlled by the size of f. So if f is bounded, then the sum of the squares of the coefficients is O of 1 uniformly in the interval. And the intervals are named I sub n, so that's what this n here is. Okay, if you don't like this talk about quantum splines, never mind. Just cut into short intervals and expand the function on Fourier series within each interval. That's all I'm doing. Okay. So this is a story in which there are three scales arise in the proof. One scale is the unit scale, lambda to the minus 0. That's the scale at which our functional really lives. There's also, before I say that, I forgot to say that I'm going to impose another condition. I'm only to discuss the proof in what I call the band-limited case. That's the case where each of the FJs has a Fourier transform that's essentially supported where the Fourier variable is O of lambda. The lambda is the large parameter that appears here. So we already have oscillation on a scale of 1 over lambda, and I'm assuming that the FJs are rather smooth on that scale as well. Okay, so that's going to be the small scale, 1 over lambda. Below that scale, neither e to the I lambda psi nor the factors fj have any significant behavior or any significant structure. They look very smooth below that scale. So we don't want to zoom in any finer than 1 over lambda. And what we do is we introduce a third scale, which is 1 over square root of lambda. So we decompose each of the fj's in local Fourier series, and we use intervals of lengths lambda to the minus 1/2. Okay, so now each of the fj's has a certain, still some possibly complicated local structure on each subinterval of length lambda to the minus 1/2, and we have many of those subintervals, so they may fit together, their behaviors may fit together in some complicated way as well. Okay, you know, at the intermediate scale, two really good things happen, and they both have to do with linearization. First of all, the oscillatory factor e to the I lambda psi, it's not in any sense nearly constant at the scale lambda to the minus 1/2, but it is essentially a Fourier monomial e to the I lambda x dot some vector c on each square of side length lambda to the minus 1/2. So the higher order terms in the Taylor expansion of psi become negligible on this scale. Okay, so we've achieved a local linearization of the phase on this intermediate scale. Second, the functions fj are not very smooth, but fj composed of phi can be regarded as a composition of fj with a linear function at this scale. So phi can be replaced by the linear part of its Taylor series on each of these appropriate subintervals of length lambda to the minus 1/2. Okay, so reducing to the intermediate scale produces two linearizations, both of which are very helpful in the analysis. Okay, so what you do now is you have three functions fj. Each of them has this local Fourier expansion. You insert all three of those local Fourier expansions into the functional. You grit your teeth, you use Fubini's theorem, you interchange sums and integrals, and you arrive at certain interaction coefficients. An interaction coefficient is the integral over a small cube q, an oscillatory factor e to the I lambda psi, and a further oscillatory factor which comes from the characters in the Fourier series of the functions fj. So there's an e to the minus I lambda to the 1/2 sum over 3j's of Fourier variable kj times phi j of x integrated with respect to x. And again, q is a square in R2 whose sign length is lambda to the minus 1/2, and these squares tile our domain. Okay, so these interaction coefficients are multiplied by 3 Fourier coefficients, and then you have to sum over 6 parameters, the 3 Fourier variables, and 3 more parameters which name these short intervals that occur in the local Fourier series of the functions fj. So we're dealing with a tensor whose size is lambda to the 1/2 by lambda to the 1/2, et cetera, with 6 factors to lambda to the 1/2. All right, now we use the method of stationary phase. The interaction coefficient is negligibly small unless the phase is nearly stationary. And nearly stationary just means that the gradient of the phase is small relative to the scale on which we're working. So that's the condition that the gradient of psi minus lambda to the minus 1/2 times the sum of its 3 terms. We have the Fourier variables kj times the gradient of phi j, and that sum should be big O of lambda to the minus 1/2. Otherwise, if it's significantly large compared to lambda to the minus 1/2, then when you do this integral out, you get a very small quantity for this particular square. Okay, and so this condition, of course, depends on which square we're working on. It can be satisfied for some squares and not other squares, and it depends on the Fourier variables k. All right, so small Fourier coefficients are very favorable. The way we see that is we pick a small auxiliary parameter, sigma. Remember that the a's, they depend on j, on an interval, and on a Fourier variable. These are local Fourier coefficients for the functions fj. And what I say is that if at least one of the 3 functions fj has the property that all its Fourier coefficients are big O of lambda to the minus sigma, so all of them for every little interval, if that happens, then the functional itself is small. Okay, so small Fourier coefficients are good. All right, and this follows because ultimately the local contribution is a sum of products of 3 Fourier coefficients. And if you have 3 numerical sequences, if you're summing a threefold product, you can majorize that by a product of 2 L2 norms. Remember, the Fourier coefficients are bounded in little L2. That's the Bessel inequality. And so you have a third factor that's left over, and you can majorize by its sup. So if one of the 3 functions has the property that its Fourier coefficients are all small, that gives us a small factor in the integral. If you propagate that through all the sums and products, you see that the total functional also gets majorized by this lambda to the minus sigma. Okay, so the case in which all Fourier coefficients are small for at least one of the 3 factors is a very good case. Okay, and of course this reasoning was used by Rauch in 1953 in his proof of Roth's theorem on the existence of arithmetic progressions of length 3 in sets of in subsets of the integers of positive upper density. Okay. This reasoning, which uses sums of products of 3 Fourier coefficients in exactly the way I did on the preceding slide, this reasoning is ubiquitous in certain aspects of additive combinatorics. All right, so now we're going to do a decomposition of our functions. For each of the fj's, we split it into the sum of the contributions of all the small Fourier coefficients and the sum of the contributions of all the larger Fourier coefficients. Okay, and we've already seen that this first part, the small Fourier coefficient part, is for our purpose very good. We're essentially done in that case. Okay. Now we have to deal with the large coefficients. The number of if you fix J and you fix one of your short intervals of length line to the -1/2, then the number of frequencies for which the Fourier coefficients are not small is controlled. It's big O of lambda to the 2 sigma just by Bessel's inequality. Sigma is a positive exponent and lambda is going to tend to infinity. So this is not so good. But if sigma is chosen to be very small, then we still win. Then, sorry about that. If sigma is chosen to be very small, we still win with the first part and we lose a relatively small amount with this second part. And so we can hope to win more than that amount that we're losing in a subsequent step. Okay, so that's what we do. So now this part with the large Fourier coefficients is a sum of relatively few summands, and we can group things in such a way that this is a sum of O of lambda to the 2 sigma functions Gj, each of which is a single Fourier mode on each of our short intermediate scale intervals. So we've reduced from local Fourier series to local Fourier monomials. We have only one term now on each of our intermediate scale intervals. So that's a much simpler situation to think about. And the price we paid for that reduction is just that we have lost a factor of lambda to 2 sigma, and so we have to gain back more than that. But sigma is as small as we like, so we don't have to gain very much. Okay, so the only this is that although we have a single Fourier mode on each intermediate scale interval, we have no information whatsoever about how those Fourier modes or Fourier frequencies vary from one place to another. So globally, each of the function fj's is still represented by lambda to the 1/2 unknown quantities, which are these local Fourier frequencies. And there's no global structure given for those at all. Okay. So here's what we've done so far. Assuming that all our functions are bounded by 1 in L infinity, we've shown that our functional for general tuples is controlled by a good term, O of lambda to the minus sigma, plus a bad term, there's a lambda to the 6 sigma, not 2 sigma, because we have 3 functions. And then we have to take the worst case for functions which are of this local Fourier monomial form. Over each intermediate scale interval I sub n, we have a Fourier coefficient, which is O of 1, times a single Fourier monomial. Okay, and so we have to consider 3 functions G, which have that structure. At scale lambda to the minus 1/2, they're very simple, but globally, they're still very complicated. Okay, and so now we need a global step. We've seen that we win unless a certain local compatibility condition is satisfied. And the local compatibility condition is that the gradient of psi is close to a sum of terms of this particular form that we saw before. And there's a precise measurement of what close means. And what we need to show is that this can't happen on too many of our small squares at length scale lambda to the minus 1/2. So what we have is really now a global problem on the domain 0, 1 squared. In this problem, you can't hope to find enough information to win at scale lambda to the minus 1/2. It's easy to see that you can lose on some small squares. You just want to see that you don't lose on too many, and that's a global issue. Okay, and so now we come to the other element of the proof, which is sublevel set bounds, which are something that's quite familiar to experts. So a sublevel set associated to a function psi is a set script E consisting of all points x in the domain of psi, at which the absolute value of psi is less than the threshold value epsilon. So that's a sublevel set associated to a function psi with a threshold epsilon. And a very common theme is that under appropriate conditions on psi, the Lebesgue measure of this, except of this set script E, is small. Namely, it's controlled by a positive power of the threshold epsilon. Okay, so that's a general theme, and on the next slide, we'll get to a specific condition under which that holds. But we're going to encounter variants of the standard theme. The first variation has to do with the notion of equivalent phases that I introduced earlier. What we're going to need to know is that an inequality, a sublevel set inequality like this holds, not just for the given phase, but uniformly for all equivalent phases. Okay, because we know that that somehow all the phases are really equivalent for our purpose, and so surely we need uniform bounds on them in order to prove anything. Okay, we're going to have another variation though, which is that our functions, the functions for which we need these sublevel bounds, are not scalar valued. Instead, they're vector valued. Namely, we have the gradient, we have the local compatibility condition, we have the gradient of psi minus another term, which I'm going to write as a sum of three functions, hj composed of phi times the gradient of phi j. And what we have is a sublevel set which says that this vector valued function is small. And we want to understand the measure of the set on which that can happen. And in this expression, the little hj's are just arbitrary measurable functions. Okay, so we have this kind of sublevel problem. And in this slide, I'm running a little short on time, so let me just say that the world's very simplest sublevel set problem is also the most subtle sublevel set problem. If you're just considering function of x plus function of y plus function of x plus y, you want that sum to be less than epsilon. Well, if you look at the case where the sum is exactly 0, you have a very familiar classical functional equation. f1 of x plus f2 of y plus f3 of x plus y vanishes identically. And this has lots of non-constant solutions, namely certain linear functions are solutions. And so in this very simplest sublevel set problem, there are lots of solutions. There's no upper bound, even for the measure of the set of points on which the functional vanishes identically. So there's some information, but rather weak information available about approximate solutions. And this all has to do with multi-progressions and Fremon's theorem, which I imagine is familiar to many of you. So for this simplest sublevel set problem, the situation is actually subtle and the available bounds are weak. Okay, but for the more complicated sublevel set problems that I'm going to encounter, things are much better. All right, so what's widely known is if you have a real analytic function which does not vanish identically, then it satisfies a good sublevel set bound. The measure of the set where it's less than epsilon is controlled by a positive power of epsilon. That's a general property of real analytic functions. There's a uniformity property. This holds uniformly for analytic functions in any compact family. So for instance, think of a finite dimensional family of real analytic functions. For instance, think of all the polynomials of bounded degree with some lower bound on some highest order coefficient. And then you have a uniform bound of this type with a positive power of epsilon. Okay, so the way the analysis goes is that we show, first of all, that if you have functions Cj or Hj, which give a relatively large sublevel set, then you can approximate them by real analytic functions within an error big O of epsilon. Well, that doesn't say anything. Anything can be approximated by a real analytic function in a large set, but they can be approximated by real analytic functions drawn from a finite dimensional compact family, which is determined entirely by the data, the phis and the phase function psi that are given. And one can do that approximation, not on the whole sublevel set, but one can do it on a set whose Lebesgue measure is bounded below by a power of the measure of the sublevel set. And the proof gives at least the 8th power, and maybe I'm being sloppy here, maybe it gives the 4th power, but it certainly doesn't get better than the 4th power. So you don't get a significant fraction of your set, but you still get a set whose size is controlled. Okay, and because I'm out of time, I won't say anything at all about the proof of this sublevel set bound. I just ask you to believe me, it's actually very simple. In the setting where you have 3 R2 valued functions, but if you had 3 scalar valued functions, then it would be much harder. Having a more complicated inequality with more components makes things enormously simpler here. So having the variation of the standard sublevel set problem makes a huge difference, and that's what makes this actually tractable. Okay, so I just want to mention related work in combinatorics of Palouse and Prindiville within the last 2 years. They established the existence of generalized nonlinear progressions in sets with positive upper density I have not yet studied and understood their work and I have not yet understood how well it's connected with the things I've told you. And finally, there's an obvious conjecture, which is if you take functionals of the type I considered in theorem A, then the theorem should work, not just for products of 3 or 4 factors, but for products of arbitrarily many, finitely many factors with the natural non-degeneracy condition that there are no obvious counterexamples. Okay, so that is what I wanted to say today. I see that I am on time, and I thank you for your attention.